Good evening. Am I audible? Yes. I'll just wait 2, 3 minutes for more people to join. Can you see my screen? Yeah, welcome everyone for the first session. So this session is mainly conducted as a part of my PMRF fellowship. So I will be doing live sessions on contents from each week of this course, Machine Learning for Engineering and Science Application, by Professor Balaji Srinivasan and Professor Ganapati Krishnamurthy from IIT Madras. So I'm doing this live session as a teaching assistant. I'm Parvati. I am a PhD scholar in the Department of Applied Mechanics and Biomedical Engineering at IIT Madras. And I'll be doing this session on every Tuesday from 7 p.m. to 9 p.m. Before we start, I will just quickly go through the NPTEL page that contains course details and other details. Yeah, so if you go to the course page itself, you can see all the details. So when you go to the NPTEL page, and when you go to the course, you can see what this course is about and the intended audience, postgraduate and also undergraduate students. And the prerequisites, some familiarity with calculus, linear algebra, probability, statistics, and comfortable with basic programming, either Python or MATLAB. And these are the two course instructors. And the syllabus for the course is given in this course layout. So you can go through the contents of the course. So in week one, they mainly discuss, I think the first 3 weeks, it's mainly about covering the prerequisite parts, the linear algebra, probability, and optimization. Um, and then we go to the different models, starting with linear and logistic regression, and then neural networks, convolutional neural network, recurrent neural networks, and then the different types of tree-based architecture, such as decision trees, random forest, then SVM, naive Bayes, etc. And then the unsupervised techniques like k-means, and then another supervised technique knn, another unsupervised GMM, uh, followed by some advanced techniques such as the autoencoders, scans, etc. LLMs are all are not covered in this course, and the reference for the course consists of the book by Christopher Bishop, Pattern Recognition and Machine Learning. This is available online. If you search this in Google, you can get the link to the textbook. You can download it. And this is also open. You can go to this you can search this in Google and you will also find the book for this one. And some research papers are also discussed in the videos, lecture videos, for which the references are also provided in the lecture video. Yeah. So another important thing is if you are attending this course for a certificate for some credit or if you want a certificate as a part of job or something, then you have to write an exam and the details of the exam and regarding the certificate and all you can find here in the NPTEL web page. And another important part is this tab called announcement. So you have to keep checking this announcement tab to not miss any of the announcements. So starting with the first few announcements. So this part it discusses regarding the date and time of exams and the session contents every week. There will be about 2.5 to 4 hour video, and there will be assignments for every week content, which is an important part of the certification. And it's a 12 weeks course. And another thing is to write the exam, you have to register for the exam before February 13th. And there is some late fee if you register late. And then some people might be doing multiple courses, and in those cases, for students who are attending multiple courses and having a date issue, you can, I think that those details are also given here. So you can request for an additional, I mean, you can request for a date change with an additional fee, and all those details are given here. Um, Yeah, so every week there will be assignment and there will be a deadline for the assignment which you have to keep track of. So that is about this announcement page. Yeah, so then another important tab is this Q&A. So So this is where the course instructors, this is where you can post any doubts regarding the videos or any session. Either the course instructor or one of the TAs for this course will be answering your questions. So this is one part of the Q&A, which will have the link to the discussion forum. You can write mail to this and you can post your questions here. Yeah, then another part is MATLAB. So you can see that in the course page on the left side where the course outline is given. You can see this tab MATLAB and you have free MATLAB access. So when you click on this link, it will go to the MATLAB uh, instruction. So you get a set of instruction. You can follow the steps to get started using the MATLAB. So you can create your own MATLAB account, MathWork account, and then for this course you can use this the online platform till the date for the course is over. And there are some sample instruction videos to learn MATLAB, which you can refer. Okay. Now, for every week, the contents, you can find the contents for every week here, week one, week two. So it will come here, it will appear here. So you can click on this and then you can see all the videos. When you click on one, it will load the video for that particular heading or topic. Then if you want to have a transcript, you can click on this. It will show the transcript. And the lecture materials for each week will be under the video. So when you click on this one, it will go to lecture material link, which you can click, and it will show the list of PDF documents that contains the slide which are used for the lecture. So the lecture materials are given here, and then the quiz. The due date for the first week assignment is on February 4th. Now you can also download the contents or the transcript as a book here. So these are the week one videos, and the week one slides are under the lecture material one. And then, so these sessions that we are doing, so these are the problem solving sessions. There is one session on Monday by another TA, and my session is on Tuesday, 7 to 9. And if you want to find the, so this recordings, so many a times people complain that they can't attend the session at 7 p.m. to 9 p.m. So there will be always a recording. You can click on this problem solving session recording. So when you click on here, we will be actually filling the YouTube so we'll be recording this session and we will be uploading it in YouTube. And we will also be uploading whatever slide or whatever questions we have prepared. That also will be sharing in a drive in the presentation folder link. So you can always access this even if you miss one session. So this is under all the videos under the book. So you can check here, click on this, and then see this Excel. And this Excel will have the YouTube link for this TA, and also this will be my session. So I'll be uploading the video for week one after today's session, and also the slides that I am using now will be shared in a folder link here. So you can check this. Okay, so that's a quick introduction to the other contents of the course. So if you have any doubt, you can ask. So if you have any questions regarding the exam and all those things, you can ask in the discussion forum. The other TA, the main TA for this course, they and the course instructors, they will be able to answer those questions. Okay. So I'll first quickly go through the contents of this week and then discuss some previous year assignment questions which can help you to solve this year's assignment question. Yeah, so the main aim of this course is to get familiar with some of the modern machine learning techniques. Even though LLM is the most modern, the course doesn't discuss LLM, but then the traditional classifiers and also advanced deep learning models, some of the unsupervised techniques are all discussed in the course, which will pave a good foundation for machine learning. And the course requires you to know a little bit of linear algebra, or at least be uh, comfortable with linear algebra, probability and optimization ideas, and a little bit of programming using Python or MATLAB would be good if you are taking this for credit. And the course has three main parts: the artificial neural network and the deep learning part, which includes CNN and RNN, and the tree-based methods, probabilistic method, and some of the advanced methods that include autoencoders, GAN, reinforcement learning, etc. The books are already available online. So, uh, starting with the history, starting with Charles Babbage, he's the one who came up with this analytical engine, and then Alan Turing has like proposed that everything can be computed using a computer. And the first artificial neuron was introduced in the 1940s, and in the Dartmouth conference is where the first time the term artificial intelligence is coined, or it was the formal birth of artificial intelligence. And in 1957 was the time when two-layer artificial neural networks was introduced. And Arthur Samuel was a person who defined machine learning as a field of study that gives computers the ability to learn without being explicitly programmed. And then there was the golden years. There were many rule-based programs that were developed. For example, to play chess, they write explicit rule for every move. And then in 1969, backpropagation was introduced. And then there were issues, there were problems with AI, there were low computational power, there were a lot of rules, and there were combinatorial explosion. And then, so it was a first AI vendor, and then came a spring. Where again expert systems were used. First driverless car was introduced. Hopfield network, backpropagation were popularized, and then again second AI winter came. There were again disappointing results. And then in 1997, there was this Deep Blue beats Kasparov in chess. And then Moore's law was proposed, that is, the number of transistors doubles every 2 years. And then from 2000 to 2012, there were many other happenings, like Google was born, Internet bloom, and this suddenly led to a large amount of data generation. And then GPUs were developed, and then from 2012 again AI spring. It's mainly the ImageNet challenge, which brought the CNNs and the use of GPUs for computation and all those things. Those started from 2012 until now. Machine learning has been blooming like anything. Till the till the point that we are currently at the development of large language model. So this is now we have better technology, and we have GPUs that can be used now, and we have large amount. We have techniques to, or we have technology to handle large amount of data. We have software and hardware, and we have many better algorithms currently. So this figure, it was taken from this page. You can check this page. It has a good history of artificial intelligence over the last 8 decades. The same thing that was discussed in the video. But over the different computations and over the years, many developments, for example, the 1956 is the time the AI term was coined, and then the perceptron, followed by backpropagation introduction. And this also show how the number of floating point units, those got increased as we moved from simple algorithms to very large neural network model. Uh, so you can check this. I'll be sharing this slide. You can check this. Then coming to what is machine learning is, there is this famous definition by Tom Mitchell on machine learning. So a computer program is set to learn from experience E with respect to some class of task T and performance measure P if its performance at task in T as measured by P improve with experience E. So to simplify this, a task can be a problem that the program needs to solve. So, for example, you want to classify emails into spam and non-spam. So that is the task that we want to solve. And how do we solve it? We solve it by learning from some experience E. And this experience E is the data or the examples from which the program learns. So this can be a database or a data set of emails which are marked as spam or non-spam. And performance measure. So once after the program learns from this experience, if its learning improves with this experience, and this improvement in the learning, if it can be measured by a performance measure. What is the performance measure? It can be anything. It can be accuracy. It can be it can give you indication of how well the program has learned from this experience. So it's like without someone explicitly programming a program to do classification of emails, when the computer learns by itself from the data that it is given, then we say that that is a machine learning problem, or it is a learning problem. Now, yeah. So some of the common terms, anything that tries to replicate the results of human cognition is artificial intelligence. It can be rule based as well as machine learning, which includes yeah. Sorry, somebody wanted to ask some question. Sorry, I thought Manish Thakur. Do you have any questions? Sorry, I thought about. Yeah, so here they talk about some of the terms, machine learning, the program that perform better with experience, artificial neural network. Uh, one of the machine learning algorithm that we will be learning in the coming sessions. Deep learning is another artificial neural network. And big data is a large amount of or a large volume of data. And we use this data to find unobvious pattern. So, yeah, AI includes, as Sir shows in the video, it includes machine learning, and deep learning is a subset of this. And there are also rule-based algorithms that comes here. And yeah, so machine learning, as I explained before, you want to do some task, but then without you explicitly program your computer or your system to do that task. you give it some examples, you show it some examples, and then the program will learn from that examples to predict or to classify or to find some patterns in the data or to solve that task. So this is the difference in classical programming. You will be given, you explicitly write. So for example, if I want to classify an email as spam, I will explicitly write if my mail contain some terms related to money, then I mark it as spam. If my mail contains, so like that, I will explicitly program every time so that my program will know when a new mail comes, it will predict based on this set of rules. But it's like we don't know, spammers might come up with new ideas, and we will not know the actual. When they come up with a new idea, we will have to explicitly again add this rule. So, when it comes to machine learning, we just give it the data, we just give it the set of emails that we have, and we just tell it, okay, from the mail, I know that this is a spam, but I don't know how it is a spam. So the machine learning model will come up with the rules that tell you whether the mail is a spam or not. You don't need to explicitly write those rules, unlike in classical programming. So when we use it is when we are unable to find some patterns, and when we have to work on some hazardous environments, or when we want our solution to use in different cases, all this time or all these for all these applications we find machine learning useful. And yeah, so the all problems here are data, and all the solutions are functions or maps. So you will have some input all the time, and you will have an output. And what machine learning model does is find the mapping from this input to output. So for example, if in the case of marking an email as spam or not spam, the input is a set of emails and the output is spam or not spam. And now, what machine learning does is come up with a function or a mapping that maps the input to the output. So this is the learning task, this mapping from input to output. Now, there are different types of learning approaches: supervised, unsupervised, and generative approaches, semi-supervised, self-supervised reinforcement. I think we will come to all of these approaches in the upcoming session. So when we discuss, like when we have those sessions, we'll be discussing these different approaches in detail. Now there are the 7 steps. There are more. There could be more than this, or there could be less. Sometimes depending on the situation. So, but again, in general, these 7 steps are the main steps. So we need data. First, we need to prepare get the data. Either it could be a data that is online, or you can collect your own data. And once we have the data, we need to do some pre-processing. The data may not be always very clean. You need to make sure that it's devoid of any issues. And then we choose a model, we will not know which model will fit our data set. So we have to try out different algorithms and then see which will or what will work for our data. So for this, we do training and we find the best model with the best parameters. And then we see how well our model did on the data. And then there is something called as hyperparameter tuning, where we again optimize the model parameters. And then finally, we predict on a data set that is not being seen by the model. And so sometimes, if it's not clear, we will be discussing these in the upcoming sessions. So there are mainly two problems in supervised learning. So classification and regression. So what is supervised learning is, one second. Yeah, you can ask the question. Sorry, one second, I'll unmute. Yeah, you can ask the question. I can't hear you. Sorry, I can't hear anything. Can you type the question? Agash Verma, you raised your hand. Can you ask the question? I think there is an issue with my side. I can't hear it. I'm sorry, I have some issue with the headset. I can't hear the question. If possible, can you type it in the chat? Yeah, so hyperparameter tuning is it's something that comes later. So when you learn different models, so for example, neural network, there will be so neural network you basically come up with a functional mapping from input to output. So if I take a symbol, for example, if I take a case of linear regression where I fit a line y is equal to mx plus b, I have parameters such as the m and x is my input, y is my output. M and B are parameters that define the relation between the input and the output. So these parameters you will not know now, but you can optimize it through some technique called as hyperparameter tuning, where you give a set of values, set of values of M and B, and then you train the model with these parameters and see how the model performs. So this is so this is a very simple example of hyperparameter tuning where you want to find the optimal parameters for your model such that your model perform well when it sees an unseen data. So this is something that comes later. That's why I didn't explain. There are many things that comes later, which we can explain in detail later, so that you understand it better. Because now when I say y is equal to mx plus b in linear regression, many people who don't have a background may not understand it. So that's why I didn't say it. Um, Akash Verma, You can do this course to learn the basics of machine learning. Job skills, it will depend on your experience, your skills, and your uh, performance in the interview. So you can do this course to get some basic understanding of machine learning. So for math work account, I have not tried this, but you can uh, write a mail in the discussion forum that I have shown before. Usually, it is straightforward to create an account in the math work. Maybe it has to do with your mail ID. So maybe you might have registered the course with the mail ID, and you might have tried to create an account in MathWork with a different mail ID. So that could be a problem. So if maybe you can try that, and then if still it doesn't work still, then you can write in the discussion forum. Slides are not visible because I'm trying to see the questions. I hope so you can, I'm lowering the hand. I hope that answered. Okay. So, coming to supervised learning. So, supervised learning is a type of learning paradigm in machine learning where you will have a data set which will have both the input and the output. That is, if you want to predict a set of email as spam or non-spam, you will have the set of email as well as the detail that whether a mail is spam or it is not spam, the category. So when you have a data set with both the input and the output, and it's like you are, it's like in supervised learning, it's like you are having a teacher which will teach you how the input and the output is and the mapping from the input and the output. So, there are mainly two problems in supervised learning: classification and regression. So, classification is mainly uh, classifying into different categories. So, for example, tumor, which can be benign or malignant, or mail as spam or non-spam, or a credit card fraud, either as a fraudulent transaction or as a non-fraudulent transaction. Or it can be a regression task where you fit like you have to predict some real number data. For example, predicting the stock market values for a certain stock. Uh, so these are mainly the two problems in supervised learning. And in this course, mainly in the first 3 weeks, these three are discussed: linear algebra, probability, and optimization. So this, the supervised learning in detail, we'll be looking from week 4. We'll be starting with what is supervised learning, what is classification, what is regression. All those things will be going in detail. So this first 3 weeks is about covering the basics, um, in linear algebra, probability and optimization. So it so the scores and the instructors they expect you to know some basics of all these core subjects which includes vectors, matrices, the different types of matrix operations, the different factorization methods, then probability, conditional probability, different optimization techniques. So some basics in these are expected to know for this course. So it will be good to cover or brush up some of these topics yourself after watching these videos. So coming to linear algebra, linear algebra is very important because many of so the data that we deal with in machine learning, it is represented in the form of vectors, matrices. Those are all numbers, quantitative data, and these are represented in the form of matrices, vectors, tensors, etc. So dealing or knowing linear algebra, the operations in linear algebra, all these are important. So, in linear algebra, when you want to represent, so a single number is called as a scalar. So, for example, when we were talking about the line y is equal to mx plus b, where m and b are parameters, and m can be a single number. The slope of the line is a single number. So that is what we call as a scalar. And vector is an array of numbers, a list of numbers, 1, 2, 3, etc. For example, if we, so all of us have mobile phones, and the mobile phones, they have many sensors inside them. One of such sensor is this accelerometer. So if we see the accelerometer data, there are many apps that can help you access the accelerometer data from your phone. So it will show this X, Y, Z direction, and each of them, each of the axis, it denotes a vector. So in the X axis, in the Y axis, in the Z axis, it's just a list of numbers. And then metrics, a good example is an image, a 2D array of numbers. And tensors, we say anything of dimension greater than 2 is a tensor. It's an array of numbers with dimension greater than 2. Uh, so there's a question, will there be any lab session? Some basics might be explained in Python uh, when we get time to discuss after the questions. I mean, after discussing the previous year assignment questions, if possible, I'll try to discuss. Yeah, so we'll be discussing these. I mean, these we'll be covering these topics today. The concept of determinant, eigenvalues, inverse, etc. Some sample problems from all this are discussed. I mean, I have in the slide. But then it is good to go through Gilbert Strang linear algebra textbook to study in detail. And that's a really good resource for learning linear algebra. So you can go through that book as well. Um, Yeah, so so as sir discussed in the video, there is a difference between the vector in physics and ML. So in physics, you also deal with it's considered as a quantity with magnitude and direction. Here also we consider the magnitude and the direction, but here we just consider it as a list of numbers when it comes to programming. So that is the difference. Now, so everything is defined as, or everything is termed as tensors here, scalars. We can call it as a zeroth order tensor, and vector we can call as first order tensor, and a matrix we can call as a second order tensor, and tensor is third and higher order tensor. So then there is another term which is called as a dimension. So dimension is the number of components in a vector. So here b is equal to 1, 2, 3, 4. The dimension here is 4. So suppose if I have a vector, a three-dimensional vector, I will have three elements in it. So b is equal to 1, 2, 3. So that is the dimension of a vector. And here the dimension of this matrix is the number of rows by the number of columns. So it is 2 by 3. So these are some basics that you are expected to know. So every matrix is represented as a transformation. So a matrix basically represent some type of transformation. So by transformation, it can be either that a matrix might uh, try to shrink a vector, or it might try to stretch a vector, or it might try to rotate a vector. So it does this kind of, every matrix does this kind of some transformation, which can be a rotation, or it can be a stretching operation, or it can be a shrinking operation, or it can be a shearing operation. So every matrix represent one such kind of operations, and that is what we call as a transformation. So a matrix represents a transformation. Yeah. So here a scalar is a single number. A vector is a list of numbers. A matrix is a 2D array of numbers. And a tensor is a higher dimensional array of numbers. A higher dimension in the sense anything greater than 2. Now, yeah, so now let's go to some example questions. So you can answer this in the chat. So the first question, uh, a grayscale image has a resolution of 28 by 28 pixel. If the image is unrolled into a vector, what is the dimension of the vector? Yeah, so this is a 28 by 28 pixel, and image unrolled into a vector means you are transforming or you are reducing the dimension of this 28 by 28 matrix into a vector. So that we do by uh, flattening it. So by flattening, we mean, so if I have an image like this, it's actually 28 on this side, 28 on this side. So we take one column, this first column, then take the second column, take the third column. So like this. So finally it will be 28 by 28. So the answer is 784. Next question, a vector has components x is equal to x1, x2, x3, x4, x5. What is the dimension of this vector? Yeah, so the dimension of this vector is 5. So if I have a three-dimensional vector, that means I have three elements in it. So if I have x1, x2, x3, x4, x5, then that means I have five elements in it. That means it's a five-dimensional vector. Next question, which of the following is a tensor of order 3? So a tensor of order 1 is a scalar. A tensor of order, a tensor of order 0 is a scalar. A tensor of order 1 is a vector. A tensor of order 2 is a matrix. So then it is this one. So a tensor which is three-dimensional. So 32 by 32 by 3. Now, next question. A vector has six components. What is its order and dimension? Yeah. So the answer is order is 1 and dimension is 6. A vector is a first order tensor and this vector has six components. So it's a order 1 dimension 6. Now consider an audio signal. So there's an audio signal from a sensor or something, and the signal is sampled at 16,000 hertz for 3 seconds. So that means there is 16,000 points generated every second. And there is 3-second data. If the signal is stored as a vector, what is its dimension? So this means every second there is 16,000 hertz data. And we have 3 seconds data. Then what is the data size? That is the question. So 16,000 hertz means, so in 1 second, you have 16,000 points generated. So in 3 seconds, you will have 16,000 into 3. So that will be the dimension. So there will be 48,000 points and it will be a vector with 48,000 numbers. Next question. A dataset contains 150 samples, each with 20 features. If the dataset is stored as a matrix with one row per sample, what is its size? So you have a dataset and the dataset contains 150 samples. Yeah, so that dataset contains 150 samples and each sample has 20 feature. That means it's like a matrix. So you have 1, 2, etc. up to 150 samples. And each sample has a feature column. So that is around 20. So 1 to 20. Then what is the size of this matrix? Hmm. Yeah. So it is 150 by 20. Is my screen changing? Okay. Next question. A batch contains 50 grayscale images, each of size 28 by 28. If each image is flattened into a vector and stacked row-wise, what is the size of the matrix? Yeah, so it is 50 by 784. The grayscale images are there, and this is flattened. So 28 by 28 becomes a vector. Uh, so from a matrix, it becomes a vector. So it is 50 by 784. Now there is one question from previous year. Consider a data set of videos where each video has 30 frames and each frame is 64 by 64 and each frame contains three color channels RGB. So if there are 200 videos, what is the tensor representation of the data set? So the data set is a data set of videos and uh, each video, so first there are 200 videos and each video has 30 frames and each frame is 64 by 64 pixel and each of the frame contains each frame contains a RGB channel. So what is the tensor representation of the data set? Yeah, so it is 200 by 30 by 64 by 64 by 3. Yeah, so I hope this is clear. Okay, now coming to some basic operations of metrics and vectors. Addition. So I think these are some basic concepts. Most of you will be knowing it, but just to show some sample questions, I am just showing the slides. Uh, Okay. So, so normally when you have two matrices, so here A is a 2 by 3 matrix, 1, 2, 3, 4, 5, 6 are the values, and B is another 2 by 3 matrix, 1, 5, 6, 1, 7, B. So to add two matrices, they should be of the same size, that is, their dimensions should match, then only they can be added. So Aij plus Bij is equal to Cij. And broadcasting is another operation where you add a vector to a matrix by repeating that vector. So, for example, if you have a matrix A, which is a 2 by 3 matrix, then you can add a vector B to this matrix A by this broadcasting operation. So what happens there is that um, this vector B will be added in the dimension along which it matches. Uh, the vector, so then you can guess what is the condition for broadcasting. So if you have a matrix of size 2 by 3, then B can be added, B can be used for broadcasting because the dimension of B, which is 1 by 3, matches with the columns. I mean, the columns, we have three columns. So you can add this along the column. So that means you can add 1, 1, 1 to 1, 2, 3, the first row, and then 1, 1, 1 to the second row, 4, 5, 6. So the thing is with broadcasting, the vector dimension should match with either the row or with the column. That is the condition. So that is what is done here. So 1, 1, 1, 2, 3, 4, and then 4 plus 1, 5, 5 plus 1, 6, 6 plus 1, 7. So you add the vector to every row here. Then matrix product. So suppose if you have matrix A of dimension 2 by 3, 2 rows and 3 columns, and another, no, sorry, this is, okay. Yeah, so this is a vector B, which is of size 3 by 1. And then you can do a multiplication between A and B only if the number of columns in matrix should match with the number of rows in the second. So if I have A and B, the number of rows is number of columns in A should match with the number of rows in B. That is the condition for matrix product. Then another one is Hadamard product, where you have suppose a matrix A, which is of dimension 2 by 3, and then another matrix B, which is of dimension 2 by 3. And again, when you do Hadamard product, the thing is that A, B, and C is of the same size. So when you have 2 by 3 matrix, when you have 2 by 3 matrices, your Hadamard product will be also a 2 by 3 matrix. Whereas in this case, in actual matrix multiplication, that is not the case. So if I have a matrix A of size m by n and B of size n by p, I get a matrix of size m by p. Okay. Then, so in Hadamard product, what you do is an element-wise multiplication. So the first element of the first matrix will be multiplied by the first element of the second matrix. Similarly, the second element with the second element in the second. So an element-wise multiplication is done in Hadamard product and will result in a matrix which is of the same size as that of the input. They all must be of the same size. Then comes the dot product. So dot product is between two vectors. So suppose if I have a vector A of size of value 1, 2, and 3, and B 4, 5, 6, and B 4, 5, 6. So what happens in dot product is you multiply the first element with the first element of the second vector and then add again. So it's like a sum of products. So 1 into 4 plus 2 into 5 plus 3 into 6. Again, the dimensions of the first should match with the dimension of the second. And it is usually written as A transpose B, and B trans A is equal to B transpose A, because finally what you get is a scalar quantity, a single number, and this is the dot product. Now coming to transpose. So if you have matrix A, which is like this, 1, 2, 3, 4, 5, 6, a transpose operation will do it will change the rows to columns, columns to rows. So whatever was row here become column here, and whatever was column here becomes row here. So that is the transpose operation. Now, inverse is so if you have a matrix A, the inverse of a matrix is that matrix which, when multiplied with the matrix A, will lead to an identity matrix. That is, it's like a identity value. So when you have uh, uh, 3 and if you want to get 1, what do? You multiply by 1 by 3. So that is what inverse does for a matrix. So consider A is the 3, then 1 by 3 will give you 1. So instead of that single scalar value, here we have a matrix. So that is the inverse. So this definition, A inverse A is equal to A inverse. This is the equal to I is the criteria for inverse, and this is for a square matrix. And also all the square matrices, they will not have an inverse. Some may not have an inverse. There are cases that will come across where there won't be an inverse. Now, for non-square cases, now when we don't have um, uh, a square matrix, we still can have an inverse for a rectangular matrix, and those inverses are some special inverses called the pseudo inverse. So you can check about the pseudo inverse outside. Or you will come across this in case of linear regression when we discuss the linear regression. Okay. Now, the first question, which condition must be satisfied to add two matrices A and B, same number of rows, same number of columns, same number of rows and columns, any sizes are allowed. So it should be same number of rows and columns. Second question, what is A plus B here? A is equal to 1, 2, 3, 4, B is equal to 5, 6, 7, 8. What happens when you add A, when you do A plus B? Yeah, so you just have to add the individual elements. So 1 plus 5, 2 plus 6, 3 plus 7, 4 plus 8. Okay. Broadcasting a vector B to add it to matrix A is possible Only if B has the same number of rows as A, B has the same number of columns as A, either A or B, both A and B. Yeah, so it is either A or B. What is A plus B using broadcasting? Yeah, so I think it is the same example that was there in the uh, slide. So if A is 3 by 4 and B is 4 by 2, what is the size of C is equal to AB? Matrix multiplication. Yeah, so it is 3 by 2. So somebody has written 6. That is not correct. Uh, it is 3 by 2. It's not a vector, it's a matrix. So here A is 3 by 2 means you have 3 rows and 2 columns. It's a matrix with some value like this. Okay. So, yeah, okay, no problem. Then the next question, 6 for C is equal to AB, which formula gives Cij? Yeah, so it is uh, C, AIK, BKJ, where this K will manage the number of columns of A matching with the number of rows of B. So the summing happens over that. If A is equal to 1, 2, 3, B is equal to 4, 5, 6, what is the dot product of A and B? Yeah, so it is 32. I hope it is clear. Which expression correctly represent the dot product A dot B? Yeah, it is both A B transpose and A transpose B. So both can give you, so it's a scalar quantity and it will give the same value. Ninth question, if A is 2 by 3, what is the size of A transpose? Yeah, so with transpose, the row become column, column become row. So if it's 2 by 3, it will become 3 by 2. Uh, Next, 10th question. Which condition defines the inverse A inverse of a square matrix A? A inverse is 0, A inverse is A inverse is A plus A inverse is I. Yeah, so it's easy. A inverse is I. Now, next question, 11th question. A sensor vector. So there's a sensor, and the sensor is generating some data, and that has a size 8 by 1. And you want to map it to something of size 3 by 1. And for this, you use a matrix called W. And the transformation is W into V is equal to U. So what must be the size of W? So W into V is equal to U. This is 8 by 1. This is 3 by 1. What should be W such that you get 3 by 1? That is the question. Yeah. So it should be 3 by 8. Let A be a 4 by 3 matrix. B is 1, 2, 3. What is the size of A plus B using broadcasting? Yeah, so the size will not change when you do that operation. So it is 4 by 3. A robot collects 12 sensor readings at each time step and it forms a vector X. So there are 12 readings. You want to map this to a four-dimensional vector. So what is the size of W? Yeah, so it is 4 by 12. A grayscale image of size 28 by 28 is flattened into a vector and then mapped to a 10-dimensional output. Uh, what is the valid size for this transformation matrix? Yeah, so it is 784 by 10. Now, one previous year question. An autonomous vehicle collect data over 1,000 time steps from 6 cameras and 3 LiDAR sensors, yielding a 1,000 by 9 matrix. You want to transform this to a single combined camera feature, two combined LiDAR feature. So for each of the 1,000 time steps, output is 1,000 by 3. So what is the size of again this matrix? Yeah. the transformation matrix. Yeah. So it is 9 by 3. I hope that is clear. Okay. Then the next question, it's also last year question. So there are two matrices P and Q. P is 2 by 4 matrix and Q is 4 by 2 matrix. The following operations are performed sequentially. So the product of P and Q is found, resulting in R. So what will be the size of R? P is 2 by 4 and Q is 4 by 2. What will be the size of R? Yeah, it will be 2 by 2. Now, next operation is take the transpose of R. Now, when you take the transpose of R, what will be the dimension of R? Transpose 2 by 2. Yes, the rows and the columns, when it is interchanged, it is 2 by 2. Then subtract the 2 by 2 identity matrix from R transpose. So, is it possible to subtract the 2 by 2 identity matrix from R transpose? Is it a valid operation? Yes, it's a valid operation because both the matrices are of size 2 by 2. So again, we get a 2 by 2 matrix. Multiply the resulting matrix element wise with a 2 by 2 matrix S, where all the elements have value 3. So it is another 2 by 2 matrix with all values 3. What will Hadamard product do? It will do element wise multiplication. And there is, when Hadamard product is done on this matrix that we get here with the 2 by 2 matrix with all the three values, we get a matrix which is of size. What will be the size of that matrix? Will there be size change when we do a Hadamard product? There won't be a size change, so it will be 2 by 2. And the matrix is multiplied by another matrix which has all the elements 3. So the option is it will be a 2 by 2 matrix with uh, each element being a multiple of 3 because you multiply every element by the element 3. Yeah. So I hope that is clear. Okay. Now coming to the next. Okay. Coming to norms. So norms will tell us how big a vector or a matrix or a tensor is. And also it tells us how close two vectors or two tensors are. That's how big the difference between two tensors is, or how close one tensor is to another, or how similar are the not how similar, that is another term. Sorry, this is like it will give a notion of length to vectors, matrices, and tensors. So it's a way of measuring length of vectors, matrices, etc. And there are some properties that norms should satisfy. That is, if the norm is 0, then the elements of the norm, the elements of that vector will be equal to 0. And the triangle inequality, if the norm of x plus y will be always less than the norm of x and the norm of y sum. And then if you have a scalar alpha, and when you multiply it by the vector, uh, and when you take the norm of it, it will be always a scaled version of the norm, the linearity property. Now, there are some standard norms which are the Euclidean norm or the 2 norm, which is the square root of, so if V1, V2, V3 are the elements in a vector, so if V is equal to minus 5, 3, 2, then V1, V2, V3 correspond to minus 5, 3, and 2. And we take the square root of V1 square plus V2 square plus V3 square plus etc. up to Vn square for a 2 norm or Euclidean norm calculation. And 1 norm is when we take the absolute value of each of the element and then we add them. P norm is when we take the pth value, the absolute value, and then take the 1 by pth of the sum of these values. Infinity norm is taking, so if I have a set of vectors, a set of uh, values as a vector with a set of value, we find which one has the maximum absolute value, that is the infinity norm. Okay, so these are, this will give you a length of, this will give you a notion of length of a tensor. Uh, Coming to some example questions. Can you see the questions? I hope you can see. So the first question is for a vector, calculate the 2 norm. So there's a vector 3, 4. What is the 2 norm of it? Yeah, so it is straightforward. It's a square root of 3 square plus 4 square, which is 5. Then the next question, one norm you have to find. P is equal to minus 532. What is the one norm? So it is 10. Now for the third question, what is the infinity norm? It's the maximum value, maximum absolute value. So it is 5. What is the Frobenius norm of the matrix A is equal to 1, 2, 2, 0? So when you take the uh, so when you want to find the Frobenius norm, we square every entry and then just take the square root. So what will we get? Yeah. So 1 plus 1 square plus 2 square plus 2 square plus 0 square. Then take the square root. So 1 plus 4 plus 4, which is square root of 9, which is 3. Okay. One question from previous year. So Z is minus 2, 3, minus 1, 0. If the norm of Z in the LP space is defined as Z1 of P plus Z2 of P plus Z3 of P plus Z4 of P, the whole raised to 1 by P, which of the following norms will give the same value as L1 norm for Z? So Z is minus 2, 3, minus 1, 0. What is the L1 norm for Z? So the same way you calculated the two norm, the one norm, the infinity norm, you calculate the two norm, the infinity norm, the zero point 0.5. It's not a so the pth norm is applicable only for p values greater than or equal to 0, sorry 1. Um, so when they have value zero point 0.5, it's usually you can calculate it, but it is usually not called as a norm. But you can calculate it here by substituting for p is equal to zero point 0.5. And then when you do this, you can see that none of them matches with the L1 norm. So the answer is actually none of the above. You can calculate each of the norm and see. Then linear combination. So linear combination of set of vectors is given by multiplying each vector by a corresponding scalar coefficient and adding the results. So if P1 is a vector of elements 1, 2, 3, and V2 is 2, 0, 3, then V1 plus 2V2 is called as a linear combination where you multiply each vector by a scalar coefficient. So for example, 2V2, 2 is a scalar and the vector V2, and adding the result with another vector which is multiplied by a scalar coefficient. So this is a linear combination. Um, so yeah, so they say that matrix multiplication can be interpreted as the linear combination of columns. So one example is shown here. So suppose V is a matrix 1, 2, 3, 2, 0, 3. And so this is just to show that it is also a linear combination of columns. So I hope this is clear. Where you take, so we have multiple vectors. We take the scalar coefficient of those, the product of that vector with the scalar coefficient, and then add the different vectors. the resulting set of vectors is what we tell a linear combination of a given set of vectors. Now coming to span, span is a set of vectors that are obtainable by a linear combination of original vectors. So span is when you have a vector x1, y1, and another vector is x2, y2. The set of all the vectors that you can generate by different combinations of x1, y1 and x2, y2 is what we call as a span. So the span of the coordinate vectors v1, 1, 0, v2, 0, 1. Yeah, I think this same question is there in the example question. So I'll come to that later. So then linear independence. So a set of vectors is said to be linearly independent if none of these vectors can be written as a linear combination of other vectors. So the vectors will be very independent. They will not have anything common between them. So for example, if we take this v1 is equal to 1, 0, this is a vector that is pointing in the x direction. And if you take v2, this is a vector that is pointing in the y direction. So there is no common points, and this is something that we can say as a linearly independent vector. So v1 is 1, 0 and v2 is 0, 1. 3 by 4, this is linearly dependent. So when you add a third vector v3, which is 3, 4, this is linearly dependent because you can write 3, 4 as a linear combination of v1 and v2. 3 times v1 and 4 times v2 will give v3. So we can say that a set of vectors are linearly independent if their linear combination alpha 1 v1 plus alpha 2 v2 etc. up to alpha k vk will result in 0 means that all these scalar coefficients alpha 1 alpha 2 etc. up to alpha k also must be equal to 0. That is, there is no scalar, no non-zero scalar that satisfies this. Then, if they are said to be, the set of vectors are said to be linearly independent. Okay. So, the first question is, what is the span of 1, 0 and 0, 1 in R2? Yeah, so 1, 0 and so when you take when you mean by taking the span, you take all the linear combinations of 1, 0 and 0, 1. So when we take all the combinations of 1, 0 and 0, 1, we can cover the whole R2, the whole 2D space. Yeah, so it is the whole of R2. You can generate every vector in R2 using the two vectors 1, 0 and 0, 1. That is the meaning of this. If alpha 1 v1 plus alpha 2 v2 is 0, has only the solution alpha 1 0, alpha 2 0, then the vectors are linearly dependent, orthogonal, independent, parallel. Yeah, so if all the scalar coefficients are 0, then we can say that the vectors are linearly independent. V1 is equal to 1, 2, 3. V2 is equal to 203. Are the vectors 1, 2 and 2, 4 linearly independent? 1, 2 and 2, 4. Sorry, this was a different question. I'm asking the fourth question. Are the vectors 1, 2 and 2, 4 linearly independent? No, because the one is a scalar multiple of other. So 1, 2 and 2, 4, they are multiples of each other. So they are not linearly independent. V1 is equal to 1, 0. V2 is equal to 2, 0. Which statement is true? They are linearly independent and span R2. They are linearly dependent and span a line. They are linearly independent and span a line. They are linearly dependent and span R2. Yeah. So V1 is 1, 0. V2 is 2, 0. Are they dependent or independent? They are dependent because one is a multiple of another. Now, when we consider them in 2D, V1 will be this and V2 will be this. So, this is the x-axis, is y-axis. So, it is actually spanning a line. So, they are spanning a line. So, they generate combinations which will happen to fall on the same line 1, 0, 2, 0, 4, 0, 6, 0, etc. So this is a line. So that's why they span a line. So they are linearly dependent and span a line. So there's a question. U1 is 1, 2, 3. Three vectors are there. U1 is 1, 2, 3. U2 is 4, 5, 6. U3 is 7, 8, 9. Are these vectors linearly independent? So here they have actually used the concept of determinant. So determinant is an operation that you apply on a matrix. It will tell you how a volume changes. So, for example, if the determinant becomes 0, then that means the matrix will kind of make the plane get squished or go to a lower dimension. So it measures how 3D volume changes under a certain transformation. And I think we know from our school lesson how to calculate determinant. So you can write this U1, U2, U3 as a 3 by 3 matrix. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now you can calculate the determinant of this matrix, and when you calculate the determinant of the matrix, what value will you get? 0. So when you get a determinant of value 0, that means that this 3 by 3 space has reduced. I mean, when you apply this transformation, it will make a space to go to a lower dimensional space. That means that there are some columns or vectors in this matrix that are linearly dependent. So uh, the answer is no, because the determinant of their coefficient matrix is zero. So when the vectors are linearly dependent, the determinant will be zero. That means that there are some linearly dependent rows or columns, and they will get cancelled. So if there is a 3 by 3 matrix and you say that the first two rows are a linear combinations, then when you find the rank, you will see that the rank reduces from 3 to a lower value, maybe 2. So then you see that the dimension of the space has reduced when you do this operation. So that means it is a linear, the set of vectors or the set of columns are linearly dependent. So determinant helps you to find whether the columns form linearly independent or dependent vectors. Okay. Then coming to trace is the sum of the diagonal elements of a matrix. Determinant we have discussed now. The invertibility of a matrix also depends. We can find it in terms of determinant. We'll see some example questions for this. For a 3 by 5 matrix, the trace is the sum of all the elements, the sum of first three diagonal elements, always zero, not defined. So you have a 3 by 5 matrix, will look something like this. The trace of this matrix will be this first three diagonal elements. So this was mentioned in one of the video. Even if the matrix is a non-square matrix, you will still take the first three or the first 10 elements to form the trace. A square matrix is invertible if and only if its rows are orthogonal, its columns are linearly independent, its trace is positive, its determinant is 1. Yeah. So a matrix is invertible only if the columns are linearly independent. Because when the columns are linearly independent, the determinant will be a non-zero value. And we need the determinant to find the inverse. So for a matrix, for an inverse to exist, the determinant must not be zero. So here a square matrix is invertible if its columns are linearly independent. A is 2, 4, 1, 2. What is the determinant of A? Yeah, so it's straightforward. 2 to 2 minus 4. Three vectors R3 form a matrix A. If one vector is a linear combination of the other two, Then determinant of A is greater than 0, determinant of A is less than 0, determinant of A is 0. Yeah, trace of A is 0. So the determinant will be equal to 0 in that case because one is a linear combination of other. Okay. So there is a vector A which is of size p by 1, another vector B which is of size p by 1, and B is I minus B A transpose. I is the identity matrix of size p by p. Then the simplest form in which the determinant of B can be written is, so for this there is something called as matrix determinant lemma. So that is determinant of A plus UV transpose is equal to determinant of A into I plus D transpose A inverse U. So using this lemma, you can solve this question. U and V here you have to find. So what you have to find is determinant of B, and determinant of B is, you can rewrite in this form. Determinant of I minus B A transpose. Now you match this to find what is U and what is V. So A is I, U is minus B, B transpose is A transpose. So now you just have to substitute it here, then find the expression. Yeah, so the answer is C. So you can substitute it. The only thing you have to remember is what is determinant of I. Determinant of I is 1. So when you substitute it there, you get. So when you expand this, you get determinant of I into something. So there you have to substitute 1, and then you will finally get this 1 minus A transpose B. C. And there is no B inverse. There is no matrix. B is a vector. So you are asked to find the determinant of B, an expression for determinant of B. So it's like when you expand this part, you get determinant of I into 1 plus A transpose I inverse minus B. So this is this part. This using this lemma, matrix determinant lemma. And then determinant of I is 1. And this part you can rewrite as 1 minus A transpose B. I inverse is also I. So 1 minus A transpose B. So finally you get 1 minus A transpose B. Ah, yeah. So it is 1 only. It's 1. 1 plus V transpose A inverse U. One question is consider a 3 by 3 matrix. Is this matrix E invertible? Options yes, because all the diagonal elements are non-zero. No, because it's a diagonal matrix. No, because its determinant is 0, because its determinant is greater than 0. So you have a diagonal matrix with all the diagonal elements non-zero. So the matrix is invertible because all the diagonal elements are non-zero. That is the correct option. I hope it is clear. It's not because the determinant is greater than 0. It's because all the diagonal elements are non-zero. The only thing is that the determinant should not be 0 for invertibility. Hope this is clear. Then there is a discussion about the different special matrices, unit vector, orthogonality. Orthogonality is when two matrices are perpendicular to each other. Diagonal matrix, the diagonal elements will be non-zero, symmetric matrix and orthogonal matrix. Then the different decomposition techniques, eigenvalue decomposition, quadratic form and positive definiteness, and singular value decomposition. So I think I'll just finish with this, and then uh, maybe in the next class I can discuss the eigenvalue decomposition question and quadratic form and SVD question. So a matrix is symmetric if A is equal to A inverse, A is equal to A transpose, A transpose is I. All diagonal entries are 0. Yeah, so a matrix is symmetric if its transpose is the matrix. Which of the following is a unit vector? Yeah, so their norm will be equal to 1. Which pair of vectors is orthogonal? Then, so two vectors are orthogonal when A transpose B is equal to 0, where A and B are two vectors. So you can see that 1, 0 and 0, 1, they are clearly orthogonal. Yeah. So I think this is clear. So in the next class, which is on next Tuesday, we'll be discussing this rest of this eigenvalue decomposition. Uh, I think two questions are there, and then this question on orthogonality. And also, the session, this week 2 session contains topics from probability. So we'll be doing some sample questions and also some of the previous year questions in probability next week, Tuesday, 7 p.m. to 9 p.m. So thank you all for attending the session.